Hello everyone, my name is Nate Zvezak. I come from University of Ljubljana, and together with my co-authors I have prepared a contribution where I will talk about the impact of the design rainfall on the hydraulic modeling results. So first of all I will say a few words about problems or issues related to the design discharge definition. So in case of ungauged catchment, so those are those catchment where we don't have any discharge data available, different procedures can be used for design hydrograph definition and design peak discharge calculations. In case of gauge catchments, so these are those catchments where we have discharge data available, the procedure to derive design discharge values is relatively straightforward, so we just need to construct flood frequency or carry out flood frequency analysis in order to define this relationship between the design discharge and return period. However, in case of ungauged catchments, different procedures can be used to define the design discharge values. Often empirical equations are used. The bad thing of these empirical equations is that often they have some parameters that have to be defined based on the so-called expert knowledge, which means that this introduces a great level of subjectivity and consequently also uncertainty in these estimations. Another approach is using hydrological modeling, so I will talk today about this approach. We should also know that most of catchments, especially small scale, so these are catchments areas up to 10, 20, 30 square kilometers are ungauged, which means that there are no discharge measurements. So why is information about the design discharge and hydrograph even needed? So for the design of different hydrotechnical structures, such as culverts, breach openings, dams, levees, and things like that, information about design discharge is needed. So, as an example, rules on road design in Slovene Pravilnik o projektiranju cest determines that bridge openings should be designed using discharge with 100 years return period if the design road has design speed higher or larger than 60 kilometers per hour, and for roads in settlements, or using the design discharge with 20 years return period in case of other road types. So, as I mentioned, I will talk about the impact of the design rainfall definition. So design rainfall is basically compound from the rainfall duration and the internal or temporal rainfall distribution, so distribution of rainfall within the event. So I will talk about the impact of the design rainfall on the hydraulic modeling results. We selected a small catchment area named Glinščica stream located near city of Ljubljana, where we are today, as a case study, and we investigated 10 different rainfall scenarios for the 10 and 100 years return period. A short description of this selected area. So Glinščica river catchment covers around 17 square kilometers. It drains into Gradaščica river, that drains into the Ljubljanica river, which goes to the Sava river, that is part of the Danube river catchment. Elevation ranges from about 200 to 600 meters above sea level. Dominant land cover is forest, followed by agriculture and urbanized areas. Since we are near Ljubljana, mean annual precipitation is around 1,400 millimeters, and estimated time of concentration is about 6 hours. So time of concentration is time that is needed that rainfall water comes from the most far part of the catchment to the catchment outlet. So in our case, this is this point. So firstly, in order to investigate the impact of the design rainfall on the hydraulic modeling results, we had to perform also hydrological modeling. So for this purpose, we used HIC HMS model that is freely available and was developed by the US Army Corps of Engineers. model calibration and validation was performed using some discharge measurements, and we divided the entire catchment into 3 sub-catchments that are shown here. Here is also a model structure. As input rainfall station, we use Ljubljana Bežigrad rainfall station that is also indicated here on a map. And for the design rainfall, we use 3 different methods that I will in more detail describe a bit later. And also a few words about the hydraulic model that we use. So we use the model from the same, let's say, company, so Heikras. Modeling was performed only on one of the 3 sub-catchments, so this is the last one that you can see here. And we use combined 1D, 2D modeling, where 2D modeling was carried out on the floodplain areas, and connection between 1D and 2D areas was made using lateral structure, which is one of the options how to connect 1D and 2D areas in Heikras. Here are also some characteristics of hydraulic model that we used, but basically we used geodetically measured cross sections for the main channel, and we use LIDAR data for the floodplain areas. Design rainfall. So we use 10, let's say, scenarios. 6 of them were connected with half curves. I will describe these half curves on next slide. So we used 3 scenarios that were using a rainfall duration of 6 hours. So this is the same as the catchment time of concentration, because this is like a rule. How should one define the design rainfall duration in case of ungauged catchments? So that rainfall duration should equals catchment time of concentration. And we used 50 percentile, 10 percentile, and 90 percentile curve. And we also tested shorter rainfall durations, so this is 2 hours, and 2 longer rainfall durations. This is namely 12 and 24 hours. We also used scenario where the rainfall intensity was constant within the rainfall event. So this is one scenario that is not very likely to occur in nature. And we also use frequency storm methods. This is like the most extreme of the 3 selected methods, where we had 3 different positions of peak rainfall. So half curves were derived based on the analysis of past actual measured rainfall data. So firstly, we selected about 15 years of rainfall measurements at different stations in Slovenia. We then divided all these rainfall events into rainfall durations, so from shorter to mid duration events and so on. And for different durations, we analyzed all the rainfall events that occurred in this selected time period. So based on all rainfall events, we derived different percentile curves. So the lower one is 10 percentile curve, the upper one is 90% percentile curve, and the green one is 50% or the median curve. So what we have actually for different stations, for about 20 stations in Slovenia, we have different half curves for different rainfall durations. So in order to derive the design rainfall, so this is this bar plot shown in this figure, we need to combine the half curves with the intensity, duration, frequency curves that are, as an example, shown here. So we need to multiply the rainfall amount with the dimensionless rainfall depth, and we need to multiply the rainfall duration with dimensionless rainfall duration. So what we compared water velocities and volume of water flowing through 4 cross sections located on the floodplain areas on the right and on the left side. So these are shown here. And we also compared the maximum floodwater extent for these 10 different scenarios. And these are results for the 10 years return period. So one can notice that differences in the maximum flood water extent are relatively large. So the minimum floodwater extent can be observed for the case with the longest rainfall duration, so this is 24 hours. And the maximum values are obtained for the frequency storm method and for the 90 percentile half curve method. Similarly, also large differences or even larger differences exist in volume of water flowing through different cross sections. So these are for cross section 1, for cross section 2, and also for maximum water velocities at different cross sections. We also investigated what is the percentage of flooded land use types in the selected case study. And these are the results for the 100 years return period. And similarly as for the 10 years return period, differences are large or a bit larger as expected because the peak discharge values are even higher. And here is an example, a comparison between the flood water extent for scenario number 6. So this is scenario with the longest rainfall duration. So this is 24 hours for the 50 percentile half curve. This is orange line, and light blue is scenario number 10, which is frequency storm method that yields also maximum water velocities. And to conclude, so what we did, we evaluated impact of the design rainfall on the hydraulic modeling results, where we use different methods to define the design rainfall, so half curves, constant rainfall intensity method, and frequency storm method. So half curves proved to be an efficient tool for assessing the design rainfall because they are based on the analysis of past measured rainfall events, and we note that selection of the design rainfall should be regarded as an important step in the hydraulic modeling procedure, because as we saw, or you saw, for the 10 selected cases and or scenarios, the maximum peak discharge values for different scenarios were the maximum values were 1.4 times larger than the minimum peak discharge values. At the same time, the maximum floodplain extent was 2 times larger than the minimum flood extent, and the maximum floodplain water velocities were even 10 times larger than the minimum floodplain velocities. So this means that even small changes or small differences in the peak discharge value can result in relatively large differences in floodplain water velocities, for example. So at the end, a forum statement, which is rainfall characterization is crucial for credible assessment of the input data for designing of hydraulic structures on small streams. And I would also like to thank you for your attention.
Nice, thank you.